Today we're going to be looking at regression, in particular simple linear regression. Okay, regression analysis is superficially similar to correlation, and in a simple linear regression there is a direct mathematical relationship, and we'll see that later. In both cases, we're looking to measure a relationship between two numeric variables. In correlation, we saw that it did not matter which variable was on X and which one was Y. Remember, we could interchange those, and the correlation value, the correlation coefficient R, and its associated p-value through the t-test hypothesis of no correlation would give us the same information. But now it matters. In linear regression, it matters which variable you have on the X and the Y. And in this case, you want to have your predictor variable as X. It's the explanatory or the independent variable. And on Y, you want to have that as your outcome or dependent variable. The line really is the model used to describe this relationship. And it also gives us information about how, as X changes, Y changes. Now, we can use simple linear regression to examine a cause and effect relationship, but it may not be sufficient by itself. But in this case, when you are doing that, it can't be an observational type study. It has to be where that predictor, that X variable, you are tweaking in order to see what happens in the dependent variable, the Y variable. So, well, not by itself, it may not be sufficient. Of course, not one study and done, but it is one way to start looking at that. Okay, we're under the general linear model, and remember I said ANOVA was under the general linear model, and so both regression and ANOVA are linear modeling, okay? And we have a cause and effect or a predictor and response, although we can also have something observational where we're observing how as X changes, Y changes in regression and ANOVA. Now, the predictor can be experimentally set. We saw in ANOVA that, maybe we're giving certain dosage of drugs, and that's a setting of the predictor. And then we were looking at means. So this is going to be a little bit different in regression in the sense that we are looking at that association of two variables that we measure and see if we can create a predictive equation. Okay, but that partitioning of sum of squares and that building of the ANOVA table is going to be here in regression, just like in ANOVA, but with a few tweaks here. Okay, so with two variables, X and Y, we're trying to see if there's a relationship between them in regression. And if there is none, knowing anything about X will give no information of Y. And what we're going to see that we're specifically going to look at a null hypothesis that the slope of the best fit line is equal to 0. Why? Because that would mean as X changes or increases in this graph that we're seeing here from 1 to 5, Y would not change at all. That would mean a slope of 0, so exactly a horizontal line. So let's just remember Y equals mx plus b. So we're using that type of equation, but there's a little bit of a tweak on how we define what we call m and b here. So the truth is there's a true regression relationship, we would assume here, okay, where the value of y is alpha is the y-intercept and beta is the slope. Okay, and y or x are variables, values of x and y. And we're, of course, doing an estimate then, where y hat is a predicted value of y. And a, instead of alpha, is the y-intercept, and lowercase b is the slope. So how do we create a line to represent the relationship between X and y. Okay, so we've created a scatter plot like we did in correlation, and we see these dots, and we want to see that they're roughly going in a linear relationship. So to create this best fit line, what we need to do is find a line that minimizes the residuals. Okay, so if we look at this graph, right, a residual is the difference between the actual y value at some given value of x and it's predicted in the line, so on that blue line there. Okay, this is called sum of, we can measure this as sum of squared residuals, and we'll unpack this more as we go. And the idea is to just keep minimizing each one of those data points and their distance from the line for those y values. Okay, so here we are back at our equation. Our predicted value of y equals b, which is our slope, value of x, plus a, where a is the y-intercept. Okay, so again, y hat is a new one. We've had y bar, x bar, meaning the mean, but y hat means it's the predicted or estimated value. Okay, so we've seen these things called alpha and beta before for type 1 and type 1 error. This is not the same thing here. It's sort of unfortunate that we're using the same symbols, but they're not the same thing. Okay, so when we want to find the equation of a least sum of square residuals line, or least squares line they call it, or ordinary least squares line, one of the things we can do is first measure the slope. Okay, look at that numerator there, covariance in x and y. That should look similar, right? We saw that in our correlation. But this time we're looking at that as a ratio of that covariance in x and y over the variance in x, okay? Because we're saying that as x changes, that relationship between x and y should change. So the slope is the rate of change of y with respect to x by 1 unit. Okay. If we've done a correlation in our data prior to wanting to do a linear regression, we'll see that our r and b value will have the same sign, and there's actually that mathematical relationship between them where the slope equals r times the standard deviation of y over the standard deviation of x. When we get the slope, it is then really easy to get the equation of our line, because this line will always go through the mean value of x and the mean value of y. It's called the centroid. And so because this line always passes through that, then we can use those mean values of x and mean values of y, and then the slope that we have calculated to get our y-intercept. Okay, and of course our y-intercept A is the predicted value of y when x equals 0. So we'll work through an example here, the example in the book with the proportion black and the lion's noses and age. Okay, so let's also look at regression and ANOVA. So in ANOVA we had total sum of squares and its associated degrees of freedom, the group sum of squares and its associated degrees of freedom, and the error sum of squares, degrees of freedom. So remember, the error sum of squares was that unexplained random variation, and that's going to be true in regression as the residual sum of squares we're going to see. The group sum of squares was sort of our explained, right? Explained variation by how we grouped our data. That's going to be seen in our regression sum of squares, and telling us about how well our model fits. And they're additive, where the total sum of squares is equal to the regression sum of squares plus the residual sum of squares, similar to ANOVA. Here's an ANOVA table showing the sum of squares values and the degrees of freedom for a simple linear regression. Okay, so that model or sum of squares groups or sum of square regression is another word for it that we just saw. It's the fit of the model, okay? It's the regression sum of squares. It's the explained variance in mean response. Okay, and we can see it on the graph over there. And so it's the predicted value of y at any given value predicted along the line, and its distance to the mean, and that's explained variation. Then we, of course, get the mean square, whereas the sum of squares divided by the degrees of freedom for that model. That's what M stands for there. And in a simple linear regression, the degrees of freedom here is always 1. Okay, and then we'll calculate an F statistic again, where it's the mean square error model regression over mean square error, or residuals is another name for it. So in that second line, mean square error, or sum of squares error, sum of squares residuals, okay, that's the unexplained variation, and so it's every value of y to its mean, so that looks similar to what we've seen before. And in this case, it's n, all the data points that we have, minus 2. Okay, so our sample size. And then, of course, we'll get the mean square error for that, which will be the sum of squares divided by its associated degrees of freedom, and that will go into the F statistic calculation. And then total sum of squares, which is the total variation in y from the mean. Okay, so the graph sort of shows that breakdown, and the table shows how we fill out, or the ANOVA table is filled out from these sources of information. And of course, if we get an F statistic, we're going to get an associated p-value. And in some cases, some people will just use that F statistic as a test of the null hypothesis that the slope is 0. And then thus, if we get a high F and a low p below our alpha at 0.05, then we know we're going to reject our null. We don't have Tukey's here or anything like that. It's just a rejection of the null that the slope of the line is 0. Okay, one more time. Sum of squares regression equals sum of squares total minus sum of squares residual. I could rearrange that. It's additive. That's the point. The total sum of squares is the square deviations of the response variable from their mean. Okay, residual sum of squares, unexplained random variation, which we've seen before in the ANOVA. The sum of square error is every data point to its own mean. And then regression sum of squares is deviations between the predicted values and the mean of y. Okay, and again, added it here, and it's the explained variation. Degrees of freedom, okay, total degrees of freedom, and minus 1. Regression degrees of freedom is 1, and that's for the estimated slope. So that's always going to be 1 in our simple linear regression. That's not going to change. And the residual degrees of freedom is the total degrees of freedom minus the regression degrees of freedom, so n minus 2. Okay, in addition to getting an F statistic as a hypothesis test of our null of the slope being 0, you'll also see in Minitab and in some other places that there's a t-test for this as well. So as we go through our example, you'll see it will give you a t-statistic, and here's how it's created. Where our slope minus our null value of 0 for the slope over the standard error of that slope. And we evaluate just as we usually do in a t-test. In here, it's n minus 2 degrees of freedom, and I just noticed I have a typo. Sorry about that. Okay, and we would evaluate that as normal. Get our test statistic, compare it to a t-critical, look at our p-value, see if it's below our 0.05 alpha level. So very similar, and I've never seen a case where the F statistic and its associated p-value and the T statistic and its associated p-value negate each other, so they should agree. So the last piece of information that we'll get in a simple linear regression is the coefficient of determination, r squared, okay? And so we got the r squared before, in ANOVA. And here in linear regression, it really tells us about the fraction of variation that is explained by the line, okay, or explained by the linear relationship between y and x. Okay, so we can see it's sum of squares regression over sum of squares total, and that was similar to what we saw before in ANOVA. And unlike R, it goes between 0 and 1 since it's squared. And in a simple linear regression, R, the correlation coefficient, and then if we use that same data in a simple linear regression, if we square it, will equal R squared of the model. Basically, the closer to 1, the line does a better job of predicting y. Okay, and so the model does a better job the closer we get to 1. Okay, and the closer we get to 0, then it's not doing such a good job because we would see that total variation would increase. So that denominator would increase as this goes to 0 versus the other way. Of course, there's assumptions of regression. The data are randomly sampled and independent. The scatter plot shows a linear relationship, so we're always going to look at scatter plots again. We'll see when we do our example. We're going to create lines here, so this time we get to do our best fit lines. At any value of x, the residuals around the line are normally distributed. The variance in the residuals is the same along the line. Okay, we'll see how we look at those. And transformations, like a log transformation, can be used here, and I mentioned this in class, to meet these assumptions. So how do we detect deviations from assumption in regression? We need graphs, okay? Because there's no way to know without these. So we're going to be looking at our residual plots, similar to what we did in ANOVA. So I want to get you used to looking at these. So these are super important in linear regression. All right, so here's an example, and it's from your book regarding residual plots. Versus fit, and again we should see that cloud of points above and below the line, and we should see no noticeable weird curvature of these residual plots. So this is one of the most important ones that we'll look at, but this can indicate that we don't have problems with normality or with equal variances along each data point. Here's what you might actually see in your Minitab output. So in the graphs above, okay, on the first one we see a scatter plot. Okay, so we've made a scatter plot. We've got a line running through here, so we're not just doing correlation, we're doing simple linear regression. So there's our 4 and 1 plot to the side of it. So we want to see those dots along the normal probability plot of the residuals. We want to see those dots close to that line, indicating normality. Okay, we want to see the residuals versus fit, like the previous slide, above and below. Often want to see sort of those dots kind of hanging around that middle pretty well, higher density around that residual of 0. Those are the two most important plots to look at in a simple linear regression. But the histogram of the residuals, again, we might be looking for weird patterns or outliers. And the residuals versus the order of the data. This is a little bit different, you know, it's independence of our observations as we saw in ANOVA. And that's sort of true here as well. What we're trying to determine is, are those residuals not associated or correlated with some other variable that we're not measuring? So kind of hard to explain, but the residual versus fit and the residuals versus order should tell us if there's some other, maybe another variable that we're not looking at that these residuals are associated with. So below, you'll start to see that more, right? Here's the scatter plot. We see something that might not be a nice linear relationship. The normal probability plot isn't too bad, but that residual versus fitted, we really start to see something. We start to see more skew in our histogram of the residuals, and the order of the data, while hard to evaluate, also tells us there's something else at play here. But again, the normal probability plot of the residuals and the residuals versus the fitted values are the most important to look at. Okay, so one of the things that we might want to do with a linear regression model is be able to predict values. Now, so if we want to show uncertainty about the line itself, we can calculate confidence bands, okay? And we're always going to be better at predicting trends in the data with our linear regression models, okay? But what the prediction interval is showing us, if we wanted to try and predict a single value of y from a single value of x, right? Then we're going to have more error and uncertainty in that. We're going to be less good at predicting overall trends versus actually saying from this x, this is the y. Even though that's what we do, we just have to, often what we might be doing in a simple linear regression, we just have to understand that we're going to have more error and uncertainty around that when we try and predict a single y from x. Also, we got to be careful to extrapolate this linear model beyond the range of data that we have, okay? We only measured the linear relationship in the data that we have, in the range of data that we have. So if we start extrapolating beyond that, we can make errors, major errors, and they may not be linear anymore. So here's a good example, and there's the poor baby with giant ears, because if we made a model of ear length of adults over the age of 30, here's our linear y equals mx plus b type equation. Ear length equals 55.9 plus 0.22 times the age. So if we did this for 0 at newborn, right, they'd have just huge ears. So poor little baby. All right, and I said this before, it's really important that you understand the choice of predictor and response. This does matter, okay? So if you experimentally manipulate one variable, then that needs to be the predictor, and the other one needs to be the response, okay? If you have not tweaked that, then you need to think about what you're trying to predict in your linear regression. And we're going to practice this with our bear data. Example from your book in the lions, and again we're going to go through this in class, but you just get different lines, and so it's really important to know who's on X and who's on Y, and why, WHY, that is. Okay, and finally we talked in class briefly about using regression to develop standard curves. Okay, and so we've seen this light absorbance to estimate the bacterial concentration of solutions. So some of you may have done this before. And we want to be able to predict from there some unknown concentration based on its absorbent. And we do that all the time. We want high R-squareds when we're developing standard curves. So you shouldn't expect standard curves with lower R-squared values than 0.95-ish around there, because again, we're trying to predict a single Y from a single X. And again, we've seen using something like log transformations are appropriate here. And that's it.